Hello there and welcome to the DevMasters session on beginning machine learning concepts. We are delighted to show you how data science and those who practice data science distinguish themselves with machine learning techniques such as supervised learning and reinforcement learning. Let's get started. In this session, we will answer questions like what is machine learning? Why is it important to know what machine learning is, and what isn't machine learning? Then we will go into the solid components of machine learning, supervised learning and unsupervised learning, and when we would use them, and when we would not. Then we will talk a little about the two more artificial intelligence-based learning techniques such as semi-supervised learning and reinforcement learning, and how those techniques take machine learning further than ever before. To start off, machine learning was first defined by the artificial intelligence pioneer, Dr. Arthur Samuel. He said in 1959 that machine learning can be defined as a field of study that gives computers the ability to learn without being explicitly programmed. This has been a core definition for a lot of those who regularly use machine learning and mainly distinguishes between problem-solving steps that might or might not require machine learning at all. We will go over some examples right now. In a practitioner's point of view, Dr. Arthur Samuels had a point. The simplest way to explain what is machine learning and what isn't machine learning is through the use of programming language's best friend, if-else statements. A regular if-else statement goes as follows, regardless of what programming language you are utilizing or formatting through. The sequence of control flows start with an if statement, where if the condition is met for this statement, an action follows. If that is not the case, then a different action happens instead. And so on, and so forth until all conditions and all scenarios are fulfilled. In traditional programming, programmers are required to decide the conditions and decide the results explicitly, and only in some languages is the luxury of a catch-all statement of else available. If the scenario is not listed, a reaction will not follow suit. This is different than machine learning, because in machine learning, the computer through statistically driven algorithms or data-analyzed methods decides the conditions and sometimes decides the results too. This is revolutionary and sometimes overlooked because not all problems require this type of method nor mince it. In a very broad example, say that you work for a company that has all 6 of the main company pillars or departments: production, research and development, purchasing, marketing and sales, human resources, and lastly but not least importantly, accounting and finance. In this chart, the DevMasters will show you how a problem can be solved or even automated by a machine learning model, and a counter-problem of when we should not consider a machine learning model and just require some core data analytics. To highlight some of the best pillars that will revolutionize companies that incorporate machine learning, we start with purchasing. Inventory of mass products and resources are at the core of some of the best companies like Amazon and Walmart. But what if your company's products have been very high in demand lately? Will you have enough to hold off on ordering more until next quarter? That is a question machine learning has to answer. In contrast, if you want to start answering that question, you first have to consider how much resources your company has right now. That doesn't require machine learning. Another pillar that will do very well with machine learning is human resources. Especially in the very complex problem of who human resources thinks will leave the company next. If you can predict how long a certain hire or a current employee will remain with the company, you can choose to act accordingly in regards to the best interest of the company to keep projects and deadlines rolling. In contrast though, to determine if you can even hire another team member to a project, you will need their expected expense that does not require machine learning and just a trip to accounting. To dive deeper into solving those previous problems, we have to consider which main two scenarios of machine learning apply to the problem we are investigating. Is it a supervised learning scenario, where we have fully pre-labeled expectations, like previous dates when we have had to order more supplies and resources due to running low? Or is it more of a supervised learning scenario, where we do not know the pre-labeled result, like which employees at that exact snapshot in the company are expected to leave the company? The two scenarios are predictive, but for two very different results and methodologies, which means that the process for both methods are also entirely different. Here are some more examples to elaborate further on the differences. We can use supervised learning algorithms to forecast sales of certain products using the previous sales of a related or a competing product. Sure, we might not know exactly the price of the immediate product in the nearby future, but having references is enough to get us started with supervised learning methods. In contrast, unsupervised learning algorithms can help the marketing department answer a question that doesn't always have a direct answer. How many types of customers do we have right now? If we tried to use supervised learning on this problem, assuming so that we have say 5 types of customers, we might risk the chance that we do not in fact have 5 customers and only 4 or maybe 6 now. Depending on the time and the product, it isn't a clear-cut answer, and that's when unsupervised learning comes in. So we move on to talking about the different methods and procedures of the two main aspects of machine learning. We start with supervised learning, which requires users and practitioners to realize what kind of problems they are dealing with. Is it a problem that only a couple of solutions that are completely differentiated from each other, or are the solutions possible within a certain range of possibilities? If the solutions are predefined to be within certain classes, like a non-spam email versus a spam email versus a promotions email versus an important email versus a personal email, then it is considered a classification supervised problem. This is because we can usually tell the difference between a non-spam and a spam email in our inboxes, same with a personal versus a work email, and naturally, we can train a machine learning model to do so also and auto-filter our emails for us. In contrast, if the solution can't be anything within a certain predefined range, like predicting the temperature for a city that is usually between 75 degrees to about 85 degrees Fahrenheit in April, if we predict any temperature outside of this range, we will most likely be wrong. This is an example of a regression supervised problem. Lastly, unsupervised learning is usually meant to find similarities within a whole group of data, so we usually use algorithms like clustering, which models if the machine were to place data into groups for us to find the differences between and come up with a conclusion. For example, say we somewhat have a guess that at this current moment, we have 3 types of customers that all have spending habits according to volume and day of purchase different. What volume is the cutoff? Or what days go with which customer is not up to us, nor should we be the ones to find out. Thus we use a clustering algorithm to tell us eventually, by the days of the week and how much they bought, they are actually of this customer type. To elaborate further, depending on how you perceive your results to be, either continuous or categorical, you will be using a different machine learning method. Continuous supervised methods involve regressions, while categorical supervised methods are classifications. Continuous unsupervised methods are called dimension reduction, where we try to deduce the amount of noise in our data by reducing the dimensions of the data. An example of dimension reduction is the portions of images of faces for facial recognition. The categorical method is what we have already talked about, clustering, where the machine attempts to put data into groups for scientists to investigate and understand, if also validate, different groups in the data. Now, moving on to the more advanced machine learning methods, semi-supervised and reinforcement learning. Semi-supervised is the method of taking data and putting it through an unsupervised algorithm first as a way of sorting and eventually using the newly sorted data as a means to allocate to a supervised learning algorithm to produce a model as well as labeled results. To help better explain, here is an example of a fraud detection engine, a very common usage of the semi-supervised learning method. Fraud happens often, but how often do we detect fraud accurately has been revolutionized using machine learning. So to create an effective fraud detection engine, we have to think before the decision of yes or no of is this fraud. We have to think about the rules that govern our decision and even the machine's decision of labeling fraud or not. This is when semi-supervised learning comes in. There are two ways we can determine the rules that help us decide if a transaction is fraudulent or not: historical data and raw transaction data. Historical data, which is featured in the upper left-hand corner, comes naturally occurring labels and red flags detected by humans to help create the rules. Historical data with all of the fraud labels also helps create a supervised learning model that will help us adjust or even add new rules without us looking over the data. But this method is very slow because it needs pre-labeled data ahead of time, which might take months or even years to detect and confirm. This is when raw transaction data comes in, being fed directly into a real-time decision model based off of the supervised learning model that has the main purpose of approving the transaction or not fraud, and not approving of the transaction or fraud. All of the approved transactions then get fed through a secondary model, an anomaly detection model based off of unsupervised learning algorithms that will now suggest more rules of fraud for humans to judge and decide to add to the rules or not. For example, say that you are buying a shirt from a mall that you have never bought from. Your transaction from your card is approved since you do have the funds to pay for the shirt, but now the transaction gets run through the anomaly detection and suggests that since you are in a new location, it might be fraud. Immediately, which is what a good company would do, you receive a text message asking if it was you who spent X amount at X store. It will go into the historical fraud data if it wasn't you, as well as fraud rules that a new location now has a higher rate of being a fraudulent indicator. If you answer it was you, the location is now added as a new location for non-fraud places and improve the model still. This is even more spectacular when you do not, in fact, have enough funds or the fraud rules have been detected as broken, so your transaction is not approved. Again, the company will contact you if this is you, and if they are successful in receiving an answer that it was not you making the transaction, the data is now a false positive and taken into the supervised learning model for better rule generation. Reinforcement learning, on the other hand, is fully real-time components that are trained real-time and supervised real-time. We initialize the process, labeled Q, and proceed through the steps of Q until we find a set of actions that will perform the action correctly as well as assess the action's results to determine the reward level and adjusts the original process of Q right then and there. For example, say we are trying to train a robot to ride a bike properly without falling off the bike. Think of the process of how we usually ride a bicycle. We first have to get into the bike, place our feet properly, then balance the bike enough to start pedaling at the same time and keep the handlebars even. Riding a bicycle might seem natural to us, because it is designed for us by us humans, but letting a robot learn how to ride one requires a little more intermediate steps to get going. So we call the individual steps as processes, and actions for each process determines a reward. So for example, a simple task for humans to get into the bike allows us to get onto the bike forward with our feet on the pedal and our hands on the handlebar. If a robot decides to get on backwards, it might succeed on placing its feet, but not have any way of holding the handlebars, thus falling over is of a higher possibility. Thus the Q process of getting on the bike results in the most positive solution or decision of getting on forwards. Now more Q processes are added in, like pedaling a bicycle, balancing the bicycle, turning the bicycle, stopping the bicycle, etc. Now riding a bicycle doesn't seem so simple. Imagine all of the things a self-driving car will have to encounter as you are driving yourself. Not so simple, but can be done naturally through reinforcement learning. Going back to regular machine learning methodologies like supervised learning and simple unsupervised learning, there are many algorithms to choose from when using deciding regression algorithms, or classification algorithms, or clustering algorithms, or dimension reduction algorithms. While each of them are their own masters in their own fields, as applied data scientists, we choose to understand what the algorithm is, how to use the algorithm, especially through packages like scikit-learn for Python, and most importantly, we understand when in the data science or data processing phases to use the algorithm, where or which industries or situations have the algorithm has already been used for, and if there is an algorithm that does the same as another, or answers the same answers in the previous two questions, which betters our decision in terms of sacrificing time or accuracy. These questions are questions that only experience and particular data scientists for particular industries and situations can answer. We find that a lot of companies usually do not have one model nor one algorithm that they use for their entire products. A well-rounded data scientist knows their industry and what problems need what situations, and if machine learning is required of them to be used or not. This wraps up our session on beginning machine learning concepts with the DevMasters. We went over when we should use machine learning, what are the differences between the two main components of machine learning, as well as introduced semi-supervised learning and reinforcement learning. The DevMasters is an artificial intelligence and data science training company that specializes in bringing to you valuable information on the topics that only applied data scientists can provide to you. We hope to hear from you for other data science topics like Python for data science, SQL for data science, and statistics for data science.